How you doing, guys? I'm Mr. Rose, and today we're going to start our discussion about simple harmonic motion. First, you may be wondering what's up with the sunglasses. I would be too. Well, I scratched my cornea over the weekend, and the bright lights hurt my eyes. But physics must go on, so here we are. Like I said, today we are starting simple harmonic motion, and specifically simple harmonic motion in small oscillations. So when you think about simple harmonic motion, people generally start thinking about pendulums swinging back and forth, or springs oscillating back and forth. But every mechanical system, and we're going to explore mechanical systems that are in stable equilibrium, every mechanical system undergoes this simple harmonic motion. So here it doesn't matter if I have something big like the prudential center, give the prudential center a kick, it starts to oscillate back and forth in a very predictable motion. Now what do I mean by stable equilibrium? Well, here I have a picture of a bowl, and on that bowl I have a little marble in there. That marble, if I give that marble a kick, it's going to start rolling up and down until it eventually settles very happily right in the bottom where it started. This would be a stable equilibrium where it has some kind of a restoring force, bring it back to where it started. An unstable equilibrium would be take that same bowl, put a marble on top of that bowl, balance it ever so slightly, and just give it a kick in one direction. That marble is going to fall down to the ground and come to rest there. There's no restoring force bringing it back. So that's what we mean by a stable or unstable equilibrium. Well, if I examine now this picture, we can picture a very common system, and it's kind of the go-to system because seemingly solid stuff like the wall of the prudential center, or maybe a triangle and a band, seemingly solid stuff all undergoes this oscillation where we have our atoms connected by these little microscopic springs. Not really, but we're pretending they're microscopic springs. And if I give that mass a kick, so I take this mass and I pull it all the way out there where I have this little dotted mass, and then I let it go, you can imagine that it's going to oscillate back and forth. Now here I've taken the liberty of labeling my spring constant K, because I'm sure we remember everything we've ever talked about in physics. Remember that a spring has a spring constant K to say how hard or easy it is to stretch that spring out. Before I did anything, my mass was in equilibrium, and when I pulled it or pushed it, doesn't matter, that obviously needs to account for Newton's second law, F equals ma. This is our rule, this is our law. So again, this spring is going to be oscillating back and forth with Hooke's law. And recall, Hooke's law is negative kx, where k was that spring constant, and x is how far I stretched or compressed my spring from equilibrium. Remember, that negative is if I'm pulling it in this direction, that negative shows the restoring force pulling it in the opposite direction. And now I want to write mass times acceleration a little bit more, a little bit AP physics-y. So we're going to say that's mass times d squared x over dt squared, my second differential order equation. So all we need to do to solve this simple system is solve a second order differential equation. Well, that's a problem. When we get to second order differential equations, we can't actually go and solve them. What we're doing is we're basically going to take a guess of how to solve that. Now, some of you may know already that looking at a second order equation like this and looking at our result of negative kx means I need to take not one but two derivatives, and my answer needs to be the negative of itself, say for some constants that aren't going to change its value. That is somewhat complicated to do. Now I personally know, and some of you might also know, that the answer has to be either an e to the alpha x, where alpha is a constant, or a trigonomic function. But which ones? How do I know other than guess and check? We're going to take a slightly different approach to that. Okay, so to continue now, moved over, I took our picture from before and I just moved it up here and I added some common labels. Here I still left my equilibrium position, but instead of just some random x value, I said I pulled my spring out to a maximum amplitude, or I could have compressed it to a minimum amplitude, but we know it's going to oscillate back and forth with those exact positions. Other things that I'm sure we remember, we need to recall things like period and frequency. Period, hopefully we remember, is the amount of time this takes to make one complete oscillation. So if I pull it to A and then I let it go, the period is how long it takes to come all the way back. One complete revolution. We measure that in seconds. Second, our frequency is just how many oscillations it makes per second. It's a unit of 1 over second or hertz. Now remember, 1 over second we've changed in the past. We've used that as cycles per second or in radians per second if we were in the right unit. And the first thing we want to do is we want to figure out a position versus time graph for this. And we're going to do that because we're taking a more common, concrete approach to solving that differential equation. So if you look over here, I have already made this graph for me where I gave my bounds of A and negative A. There's my amplitude on either side. And I know that if I pulled it to some function A, I'm starting at A. Then I know it's at equilibrium position. It came back down to 0 where I started. Then it went all the way back down to negative A, and that's going to continue to repeat. So then when I connected my dots here, I see a function that I'm sure looks familiar. That function that hopefully looks familiar to you is a cosine function. So I know that my period, the time for one complete cycle, is there until it gets all the way back to that top part A. So I know my position, this should be a position as a function of time, is equal to A, that's my amplitude, times the cosine, the function that I recognize, times something that I'm not sure of yet, times t. Well, what is that something that I'm not sure of yet? Well, if I remember from math that my cosine function has a period of 2 pi over t. So I'm going to take that 2 pi over t, I'm going to plug it right in there, and now I have a general expression for a position of any oscillating mechanical object undergoing simple harmonic motion of x equals a cosine 2 pi over t times t. Well, this to me, now I have a period here in seconds and a time in seconds, which tells me something very important. It tells me that at any integer value of period, 1 period, 2 periods, 3 periods, my t's are going to end up canceling, and I'm going to end up with x equals to a cosine of 0. Well, I know cosine of 0 is 1, which shows me that my maximum displacement is going to be for any integer t. 1 period, 2 periods, 3 periods, it's always going to be a. It's always going to get back to either a positive or negative value of a, which by definition is harmonic or repetitive motion. Now, I know what you're thinking. You're thinking to yourself, I've thought and I've seen that 2 pi over t before, and you're right. 2 pi over t is just our omega, our angular velocity. Well, here we're using our angular velocity as kind of an angular frequency. They are close enough to the same. There are some small differences, but we know our angular frequency could be 1 over seconds, revolutions per second, radians per second. If we're in our sines and cosines, it's probably going to be radians per second because we know cosine and sine by definition are a function of that radian. So now I have a position graph, and I'm thinking to myself, great, I'm done. No, I'm not done yet. If I come back over here, I know I'm still trying to solve Newton's second law. So I'm going from position now to velocity. Well, I know the velocity, if I'm going to do it graphically, is dx dt, which is taking a slope. I'm going to come back to that momentarily. I want to do it not graphically, but mathematically, because we do know some calculus, so let's use some calculus. I know that my velocity, the dvt, and here's my x variable, is just a cosine omega t. I plugged in my omega for 2 pi over t. And now when I take the derivative of this, I hopefully recognize the chain rule. So I know a is a constant, a comes down. The derivative of cosine is a negative sine. The inside stays the same, omega t, times the derivative of that inside, which is omega. I rewrite that. Now I have v equals negative a times omega sine omega t. This is my velocity equation, where my maximum velocity is negative a times omega. Well, if I come back over and I wanted to do it graphically, I know that derivatives mean taking the slope. So I'm going to look at all of those points. And I know right here, I've got a slope of 0, so I'm starting at 0. Here, I've got a very negative slope, got a negative value. Here, I've got another slope of 0, positive slope, and I continue, and when I connect those dots, I see something very familiar. I see a sine function. And I see a sine function that looks like it is shifted, almost a phase shift. Remember that language. A phase shift of pi over 2. I have my maximum value of a times omega, of negative a times omega. And now here I'm very happy with my velocity versus time graph. Well, I'm almost there, but I'm not quite there yet. I can go one more time graphically, but again, I want to use the calculus we know. So now to solve my second order differential equation, I'm coming all the way back to find acceleration. Well, I know acceleration is the derivative with respect to time of my velocity component. So I have my negative a omega sine omega t. And this time I'm going to do it in one step because it's the same exact math. The derivative of sine is cosine, so my negative stays the same. I have negative a times omega. Now remember, it was a chain rule, so when I take the derivative of the inside, I would have an omega. Omega times my omega is omega squared. So my acceleration is negative a omega squared cosine omega t. Now if I remember, I was looking for a second order differential equation that when I started with something, a cosine omega times t, I got back a negative of the same thing, save for some constants. And that's exactly what we just proved. Now when I go and throw that into my graph, I have my now acceleration maximums, negative a squared and a squared. Here I start on a negative, so I'm starting negative. I have a slope of 0, a positive and a positive. And we go through the same steps. And look at that. I've got a positive cosine for position, a negative cosine for my acceleration graph. So what did all of that do? What did we actually show? Well, let's go back and what did we do? First of all, I started with my Newton's second law. F equals ma. I substituted in my second order differential equation and I said force is equal to mass times what we just found for acceleration, negative a omega squared cosine omega t. Now we know F is equal to negative kx because this is a spring constant. The spring just oscillating back and forth. Every system we can, almost every system, we can use this as a model for. So now I'm going to sub in what I got for x. I have my spring constant k, negative k equals a cosine omega t, which is equal to the mass, times negative a omega squared cosine omega t. And now what do you start to see? You start to see I can cancel out a negative. I can cancel out a negative. I can cancel out an a. I can cancel out an a. Cosine omega t, cosine omega t. And all of a sudden, all I have left is an m, an omega squared, and a k. That shows us a really important thing. That tells us that omega squared, my angular frequency, is only related to a spring constant and a mass. So angular frequency, something that has time built into it, isn't time dependent. That is a huge, huge, huge thing to say. And then our last thing is I have labeled 3 and 4. 3 and 4 is my position of any oscillating system with respect to time. I can find this position in any oscillating system of a cosine omega t plus phi. And I know I just tried to throw that phi in there without telling you. Remember what I said. We started with cosine just as an arbitrary constant, an arbitrary function rather. I could have just as easily started with sine. This is shifted, a phase shift of pi over 2. Well, this phi is just a phase difference depending on where we start our clocks. We'll get to more on that phase shift next time. Remember to like, comment, subscribe, and I'll see you next time. Thanks for watching.